myself Nipun Agarwal. For the oral presentation for the course Advanced Digital Communication, I'll be explaining the concept of Rake receiver, which harnesses a multipart diversity in a direct sequence bit spectrum. The oral presentation is divided into three parts. The first part, which is this one, presents the introduction to the concept of Rake receiver. The second part dives deep into the derivation of the Rake receiver decision statistic, and the third part would present a MATLAB simulation for the Rake receiver. So in a traditional wireless communication system, signals transmitted from a transmitter reflect off multiple objects like buildings and terrains and create a multipath channel. The receiver receiving the signal sees a superposition of multiple attenuated and phase shifted copies of this transmitted signal, each of them arriving with a different complex gain and with a different delay. In a traditional narrowband system, these overlapping signals cause a destructive interference at the receiver, which leads to a severe performance degradation and is known as fading. To combat this, there is something called as direct sequence spectrum, which uses a transmission bandwidth that is significantly larger than the underlying information rate. And by using a spreading sequence with a good autocorrelation property, these time-shifted copies of the signal became approximately uncorrelated. This results that instead of blending of all these copies into a destructive interference, the wideband allows the receiver to effectively separate and resolve all these signals into individual multipath components. The Rake receiver then turns this multipath fading into a strength by summing up all the energies from the scattered multipath components. It utilizes the multiple correlators, which are referred to as fingers, where the ith finger is synchronized to the delay of the ith multipath component. The output from all the fingers are aligned and some using the covariant maximum ratio combining. And this technique provides a massive diversity gain, which vastly improves the signal to noise ratio and the error probability compared to the standard receiver. Okay, so in this part of the video, we would be deriving the Rake receiver decision statistic. So to derive the Rake receiver, we first need a mathematical model for the wireless environment. In this case, I model the channel as a linear time invariant system, so which is given by HT. So here L represents the number of independent resolvable paths, and for each component I, we have a complex gain alpha I, which accounts for fading, and a delay associated for each component represented by tau I. Next, we want to transmit a direct sequence spectrum signal UT. And it is convolved with the channel HT as given here. So let us look at one symbol, BM. And here ST represents the spreading waveform. So the direct sequence spectrum channel UT is given by this. And again, BM is a single symbol, the MH symbol, and ST is a spreading waveform here delayed by the time period capital T. So the received signal now becomes yt equals to ut, the ds spectrum signal channel ut, convolve with ht, the channel, plus some awgn noise. Writing it out completely, we get so the received signal yt is the sum of L delayed and scaled version of our spreading waveform ST. Plus obviously the AWGN. Now we need to find the optimum solution. So let's assume that we have S cap T as and we can define the summation as our effective spreading waveform. So this is actually the actual shape the receiver would see after the channel has distorted our signal. And as we know from communication theory, the optimum receiver for a known signal in AWGN is a match filter. And the decision statistics for a matched filter can be given as so the decision statistics Z is found by correlating the received signal yt with the conjugate of our effective spreading waveform, which is S conjugate t minus m capital T. So this particular decision statistics will maximize the SNR. And now let's substitute our definition of the effective waveform back into this integral to see the Rake receiver structure. So this now becomes so we notice that the sum inside the conjugate, we can pull the sum outside and the constant gain alpha I outside the integral, and this will now become since this was a complex gain, so the conjugate of the gain is there. This is so each integral zi represents a single finger or the ith finger of the Rake receiver. And correlating the input with a specific delay tau I. And the final step is actually combining all the fingers. So rhythm actually now becomes a closed form expression. So here we actually weigh each finger by its conjugate gain alpha I, and this is known as the maximum ratio combining, and it ensures the strongest part contributes the most to our decision. Also, there are actually three critical points that I wanted to point out for this derivation. So first of all, this derivation only works when the chip rate is high, and for the direct sequence spread spectrum, the time difference between the paths should be greater than one chip duration for this to work. And since the paths are approximately orthogonal, it allows the finger to separate them. The second point is by summing these paths, we aren't just getting more power, we are also protecting ourselves against fading. So when we sum all the independent paths, it is very highly unlikely that all the L paths are in the deep fade at the same time. There would be at least one path by probability that won't be in like a deep fade situation, and that part would give us the required SNR and the required channel information. Finally, just to provide an analog, um, the reason why it is called a rake receiver is that each of the individual fingers rakes up or consolidates the energy from different multipath component and pile up against each other, so that in the output we get a summation of energy from different independent paths, and so that we get the required SNR that we require and that we want. Okay, so in this part of the video, I'll be showing a very simple MATLAB simulation for multipath resolution and diversity gain using the Rake receiver. For this simulation, the parameters are chosen as, I've taken the processing gain as 31. I've taken 3 independent multipath components. The simulation would be executed over an SNR range of 0 to 14 dBs, with each SNR points having the number of bits as 10 to the power 5. The delay for each path of the multipath component would be 0, 4, and 9 respectively, and the powers for each path would be 0, -3, and -6 dBs respectively, which would be changed into linear scale using this formula. Okay. So in the first figure, we actually look at a channel impulse response. And here I have simulated 3 paths with 3 different delays and powers at delay equals to 0, delay equals to 4, and delay equals to 9. And this is the scattered energy that we need to collect using the Rake receiver. These 3 stems represent the multipath delays at 0, 4, and 9 chips, which creates a frequency selective fading that usually destroys a narrowband signal. In our case, this actually would be the source of the diversity. In the second figure, I run the correlation at the receiver. Because the processing gain sequence has a sharp autocorrelation, we see that the 3 distinct peaks, these peaks correspond exactly to the 3 fingers. And we notice that the wide bandwidth allows us to see the 3 individual paths. Each finger of a Rake receiver is simply a sampler that grabs values as the specific red dots. This allows the receivers to distinguish between the primary signal and its echoes. With figure 3, we see the constellation improvement from a single path receiver to a multipath Rake receiver. We notice that the constellation on the left, the points are actually scattered and they often cross the decision boundary due to fading and noise, which causes a bit error. But looking at the Rake receiver output on the right, after we apply the maximum ratio combining, the point cluster uh, moves much more away from the decision boundary and is tightly packed. Here, the receiver is literally taking up the energy from all the three independent paths to strengthen our signal. Finally, we look at the bit error rate. The red line represents the performance without diversity. It shows a very shallow, almost a constant curve, which means that we need a huge amount of power to get low error rate. The blue line is the output of the Rake receiver, and the steeper slopes indicate that we have achieved a diversity order of 3. This also confirms that the Rake receiver effectively mitigates the impact of fading by exploiting the multipath components of the channel.